All right, let's go through another review. There's a previous one here on Edpuzzle, and this is our second one. For this first problem, we have an exponential equation. And when we look at exponential equations, it's probably going to be easiest if we can rewrite the equation so that they have the same bases. And so with a little bit of playing around, you can look and see that you can rewrite the number 32 as 2 to the 5th power. So that's exactly what I've done here. I've written 32 as 2 to the 5th. Well, now we have a property of exponents that they're called one-to-one functions. What that allows us to do, if the numbers are the same and the bases are the same, then these exponents must be the same. It's incorrect to say that these bases cancel, but I know that's how students think about it. So anyway, this 3k just has to represent the number 5. So now divide each side by 3 and you have your solution. Alright, so let's go to the next one. Now this one, we're going to try and do it in the same way, but it is a little bit more complicated. On your paper it may have said equal 1, and I thought, well, hey, let's make this a proportion. And one technique to solve proportion is to cross multiply. That way, after my first step, I won't have a fraction anymore. Some people are have a little bit of anxiety about fractions, so the quicker maybe that we can clear this fraction, the easier it will be for some. So if we multiply along this, if we multiply along this diagonal and we multiply along this diagonal, what would we get? Alright, so here we get the 64 raised to the 2r minus 2 times 1, and the other diagonal 16 times 1. So now we have an equation that doesn't have a fraction. Let's try and do like we did last time and rewrite these with the same base. We have a couple of choices here. We could write it with the same base of a 2, because 2 to the 4th power is 16 and 2 to the 6th power is 64, or we could rewrite it with a base of 4, and I believe that's what I did. Yeah, 4 times 4 is 16, and 4 times 4 times 4 is 64. So now I have an equation that's going to give me the same solution set as my original. Step by step, I'm trying to get it so I can get the variable by itself. When I have an exponent, when I have a power raised to a power, we multiply these exponents. So I need to take 3 times this binomial. So each term in the binomial gets multiplied by 3. And the 3 times 2r gave me 6r, minus 3 times 2 gave me 6. Well, now we have the fact that the numbers are the same because we have this equal statement. And we can see the bases are the same. So since it's a one-to-one function, the exponents must be the same. This is just a two-step equation. Add 6 to both sides, divide both sides by 6, and you're going to have your answer. When I add 6 to both sides, 2 plus 6 is 8. When I divide by 6, I get a fraction, 8 over 6, but I notice that those are both even numbers. I can reduce that fraction, and my final answer, 4 over 3. Alright, so in this next one, we have another exponential equation. But this time on the left-hand side, we have 2 terms. And whenever we have 2 terms, let's focus our attention on the term that contains our variable. We want to get that term isolated by itself, so we're going to add 5 to both sides. When we do that, when you add 5 on the left-hand side, well, that cancels with the negative 5. I mean, that's why we did it. And 6 plus 5, 11. So now I've gone as far as I can go with just my properties of equality, and I need to think about an inverse of an exponent. Well, I can't rewrite these with the same base, so I'm going to take the log of each side. Now I can choose any base that I'd like, but if I'm going to go to my calculator and give a decimal number, then I'll want to choose either log base 10 or log base e. Log base 10, we call it a common logarithm. Log base e, we call it a natural logarithm, and on the calculator it says ln, whereas the common log button just says log. So most of you seem to prefer the log button, and here it doesn't make a difference, so I took the common log of each side. What that allows me to do is to move this exponent, this negative 2k, by the power rule. of logarithms, those properties of logarithms that were on your reference sheet, we can move that negative 2k out in front of this logarithm as multiplication. So now on the left-hand side, I'm multiplying two things together. The first factor here, well, actually 3 with the negative 2, but I've grouped this negative 2 with the k. That's what I want to get by itself. I want to get rid of this factor of log of 12, so I'm going to divide both sides by the log of 12. On the left, when I divide by log 12 divided by log 12 is just 1. So I'm left with the negative 2 times k. On the right-hand side, I have the log of 11 divided by the log of 12. So now, I'm going to multiply both sides by... To divide by negative 2 is the same as to multiply by negative 1/2. So that justifies putting this 2 in the denominator. And now the negative sign, I wrote it here in the numerator. I could have written it in the denominator. I could have written it out in front of the fraction. I now go to my calculator. I key that in, and I get, I believe it said to round to the nearest 10,000th. That's 4 decimals. I fixed my calculator to round for me, and so my final answer for this is negative 0.4825. So I hope I keyed that in correctly into my calculator. So now I have a similar problem, but it is a little bit different. The base here is e, whereas last time the base was 12. All right, that's going to come into play in just a minute. On the left-hand side, I see two terms. The term of interest is that first term because it contains my variable. This is what I want to get by itself, is this first term. The inverse of adding 4 is to subtract 4. If we subtract 4 from both sides of the equation to balance the equation, on the left-hand side, the 4 minus 4 cancels, and 29 minus 4 is 25. Well, now on the left-hand side, I have two factors. I have this factor of 8 times this e raised to the 9k plus 1. Well, it's this factor of e raised to this 9k plus 1 that I want to get by itself. So to undo this multiplication of 8 times this, I'm going to divide both sides by 8. So on the left, 8 divided by 8, that 8 just cancels. And on the right, since 25 is not divisible by 8, I just wrote it as an improper fraction. Later, I'll just key it in the calculator and let the calculator do the work. So now, this time I need to get, just like before, this exponent down out in front so I can take the log of each side. But since this base is e, I'm going to find it much easier if I take the natural log of both sides. When we take the natural log of both sides, because this natural log has a base of e, and this base is e, why, this just simplifies to the exponent. Remember, e raised to what exponent gives you e raised to the 9k plus 1. This logarithm equals an exponent, so the exponent has to be 9k plus 1. I took the natural log of the left-hand side. To balance the equation, I had to take the natural log of the right-hand side. So now I'm back on familiar territory that I can add and subtract or multiply and divide both sides of the equation to get the variable by itself. So we refer to this as a two-step equation. First I'll subtract 1 from both sides and then divide by 9 and I'll have my answer. So let's take a look at that. When you subtract 1 from both sides, on the left you're just left with that term of interest, that 9 times k, and on the right hand side I just left it with I didn't want to key in and get a decimal approximation yet, because if I did that, then later on I could have round off error in my problem. I'm just going to leave it as the natural log of 25 divided by 8, and I can key that into my calculator at the very end. So now to get k by itself, we divide both sides by 9. And now I'm ready to key this in the calculator, and when you do it, make sure that you put your whole numerator enclosed in parentheses. And don't forget to close the parentheses after you key in the 25 divided by 8. So if you do that on your calculator, if I did those things correctly, I got 0.0155. It's awfully easy to accidentally key it in the calculator wrong. You don't want to do all this work, get to that point, and then make a calculator error. Alright, so now we have what looks to be a little bit more complicated of a problem. on the left-hand side, we have a fraction, and of course, students, most of the time have some anxiety about fractions. They don't really like them all that well. But the one thing that I notice is I've got a 5 here on the right. 25 is a power of 5, 5 squared. You can play with your calculator and see that 5 to the third power is 125. So I'm going to rewrite this entire equation so that all these bases are some power of 5. The 125, I can replace it with 5 to the third power. Looks different, but it's still the same number. And since 125 is raised to this negative 4x plus 5, this 5 cubed will be raised to the same exponent. Same down here below, the 25 I can write as 5 squared, and it's going to have the same exponent. I've just replaced the 25 with 5 squared. I'm still doing the same thing to 5 squared that we did to 25, and that's raise it to that exponent. The right-hand side, I've got the 5 that I wanted, so I just left it alone. Now, we have a power raised to a power, so we're going to multiply these exponents. When we take the 3 and everybody inside, here both of these terms get multiplied by 3, and now all 3 of these terms get multiplied by 2. When I do that, this is what I get. The 3 times each term, negative 12x plus 15, and 2 times every term in that trinomial, I get 2x squared minus 10x plus 2. Well, when you have division, what we'll do with these exponents is subtract them. Had we had multiplication, we would have added the exponents, but we've got division. So it's this exponent that's in the numerator minus this exponent that's in the denominator, and I definitely need to subtract the entire denominator, not just my favorite term or the first term. So I need those parentheses. All right, so when I have this negative 12x plus 15 minus this trinomial, what I got was this quadratic, 5 raised to the negative 2x squared minus 2x plus 13. Now, on the left-hand side, I have a base of 5, and on the right-hand side, I have a base of 5. And, of course, the 1 is implied. 5 is equal to 5 to the first power. Since these exponents are one-to-one functions, then if the numbers are the same and the bases are the same, the exponents must be the same. So I set this exponent equal to the other, and I have a quadratic equation. I'm familiar with quadratic equations. I know that if I identify A, B, and C, I can use a quadratic formula, or if sometimes we can factor them. So the first thing I want to do is make sure this is in standard form by getting everything on one side and 0 on the other. So what I've done here is moved everything to the right-hand side. I've added 2x squared. I'm going to add a 2x. I'm going to subtract 13. When I do that, these first two, whenever a term changes side of an equation, it changes sign. This was on the left. Now it's on the right of the equality. On the left it was negative, and on the right it's positive. And here, when I subtracted 13 from each side, 1 minus 13 gave me a negative 12. Well, before I jump in and try to either use the quadratic formula or a factor, I notice that all of these numbers are even numbers. I can divide everything by 2. On the left-hand side, 0 divided by 2 is just 0. And on the right-hand side, these factors of 2 cancel, and negative 12 divided by 2, well, I've got minus 6. So now with the leading coefficient of 1, it's easier to factor, and hopefully you can see, since the last term is negative and the middle term is positive, the opposite signs, that x plus 3 times x minus 2 is equal to this trinomial. So we get these two possible answers. Now let's go back and look. Okay, it was an exponential equation. An exponential equation has a domain of all real numbers. So I'm never going to have an extraneous solution for an exponential. Now when we'll see for logarithms, the logarithm does not have a domain of all real numbers, so it's possible that you could get values of x that are not in the domain, and we would call those extraneous solutions. But for an exponential function, you'll never have an extraneous solution. If one of these didn't check, it's because I've done an arithmetic error. The technique will always provide the correct answers if you've done that technique correctly. If we accidentally make an error in factoring or a sign error or some other silly type of error, it's going to follow through to the end of the problem, and most likely one or both of these numbers will be wrong. But that doesn't mean it's extraneous. For an exponential function, it'll never be extraneous. Now, like I say, it could be that we make a mistake. The next problem, we've got a logarithm. So here we do have, on our final answer, we do have to plug it in and make sure that we're not taking the log of 0 or that we're not taking the log of a negative number. On the left-hand side, I notice that I have two logarithms. They both have the same base. One of my properties of logarithms say that if you're adding two logarithms of the same base, you can write it as a single logarithm. So we look at our reference sheet and see that we only have to multiply the arguments together. 4 times this quantity 4x squared plus 8. When I multiplied those together, the 4 times 4 gave me 16. The 4 times 8 gave me 32. Well, now I have an equation that's referred to as a log equation. I can't really, at this point, subtract 32 from both sides, and then I definitely can't divide by 16, because this doesn't mean log times this. This is a function. I need to do the inverse function. Well, actually what I need to do is use the definition of logarithms, I should say, rather than inverse, and write it as an exponential. The inverse of a logarithm is an exponential, but I'm just going to change the form of this equation. The base is 9. A logarithm equals an exponent, so 9 raised to the second power is equal to this argument, 16x squared plus 32. On the left-hand side, 9 squared is 81. On the right-hand side, I have two terms. I want to get the term that contains my variable by itself, so I'm going to subtract 32 from each side. 81 minus 32 is 49. Well, now to get the x squared by itself, that we want to undo this multiplication, and the inverse of multiplication is division, so we divide both sides by 16. What that will do is, I've just written the variable on the other side now, over here on the left. 16 divided by 16 was a 1, so I just have 1x squared. And 49 divided by 16. Well, now to get rid of this exponent of 2, I'll take the square root of both sides. Alright, now I need to introduce a plus or minus sign when I'm taking the square root. And when I'm taking the square root of a fraction, I can take the square root of numerator and denominator separately. The square root of 49 is 7. The square root of 16 is 4. And like I say, there'll be two answers here, positive 7/4 and negative 7/4. If you plug the negative 7/4 in, when you square it, it's positive, so I'm not going to have an extraneous solution. Alright, on the next one, we've got a similar problem, but you'll notice on the right-hand side we had a number 2 on the last problem, and on the right-hand side here we have a logarithm. So it is a little bit different. On the left-hand side, we can condense these two logarithms, because it's subtraction, as division. Log of the numerator minus log of the denominator. I can write it as a single logarithm. Numerator is 7. The denominator is 4 minus 4x. Now, this time, again, exponential functions are one-to-one functions, and so are logarithms. So if these two numbers are the same, and the bases are the same, then these arguments have to be the same. This 7 divided by 4 minus 4x, that fraction has to represent the number 10. So we set it equal to 10. And since it is a fraction, I wrote 10 as a fraction, 10 over 1. So I'm going to cross multiply. This equation is referred to as a proportion, and to cross multiply is one technique to solve proportions. So we're going to multiply along this diagonal, and we're also going to multiply along this diagonal. When I multiply along the gray diagonal, I get 10 times this 4 minus 4x, and 7 times 1, well, that's 7. So now some people may distribute to get the x by itself, but since I have two factors here, and this is the factor that I'm interested in, I actually chose to divide both sides by 10, and when I did that, I now have that factor by itself, and that factor has two terms. Well, I'm interested in the second term here. So to get rid of the first term, to get rid of that 4, I'm going to subtract 4 from both sides. Now I couldn't resist that I have 7 over 10 minus 4. I'm going to look at that 4 as 4 over 1 and multiply it by 10 over 10 to get a common denominator. this is 7 minus 40 over 10, and 7 minus 40 is a negative 33. So on the right-hand side, this subtraction results in negative 33 divided by 10. I'm now going to divide both sides by a negative 4, so I'm going to put that negative 4 in the denominator. The negative over the negative signs will cancel, and I'll have 33 over 40 as my final answer. If you plug it in, the 4 minus 4 times 33 over 40, the 33 over 10, 3.3, 4 minus 3.3 is positive. This is not going to be extraneous. This difference of 4 minus 4 times 33 over 40 is a positive difference. All right. Here, they've just given me right away that these two logarithms are equal. So since the bases are equal, and this is a one-to-one function, these arguments have to be equal. So we can quit. Now, it's incorrect to say that the logs cancel, although I know that's what students see. That's the description of students. Technically, it's incorrect, but the end result is the same. So I don't want to hear you say that you canceled each terms, but for right now, if that gets you to the correct answer, then I'll let you think it silently. So here I have this argument 2p plus 2, 4p minus 8. Collect the p's on one side and the numbers on the other. So it looks like I subtracted 2p from both sides to avoid a negative coefficient. Then I'm going to add 10 to both sides and then divide by 2. And I get that p is equal to 5. And I plug this in, and 4 times 5 is 20, and 20 minus 8 is definitely a positive value. I have to be cautious when I saw that minus sign. If this first term is smaller than 8, then that subtraction would result in a negative number, and you can't take the log of a negative number. In the next problem, I'm adding two logarithms together, but it's equaling a constant. It's not equaling a log, so I'm not going to have the situation where I'm using the one-to-one function. I'm going to have to rewrite this logarithmic equation to an exponential equation at some point. When you're adding two logs together, you can write it as a single logarithm if you multiply the arguments together. 3 times 3x squared gives me 9x squared. So on the left-hand side, I have the natural log of this 9x squared, but on the right-hand side, I just have the number 2. So I know that I can't say that 9x squared equals 2 because that would just simply be ignoring this ln, this natural log function. I can't ignore the function. What I can do is rewrite this equation. This natural log has a base of e, a logarithm equals an exponent, so I can write this equation, or rewrite this equation as e squared equals 9 times x squared. I need to get the x squared by itself so that I can take the square root of both sides. The inverse of multiplying by 9 is to divide by 9. If I divide both sides, and here I wrote the x squared on the left, I divided by 9, and 9 divided by 9 was 1, so I just had 1x squared. And over here I had e squared over 9, but I wrote it on the right-hand side. Don't let that bother you. To get rid of this square, we take the square root of each side. When we take the square root, we introduce a plus or minus sign. And the square, when you have the square root of a fraction, you can take the square root of the numerator and denominator separately. The square root of 9 is 3. The square root of e squared is just e because that had an exponent of 2, so therefore the base comes out of the radical. Don't forget to put the plus or minus sign. Now, does the minus sign check? Well, when you have this negative e over 3 and you plug it in, the only variable we have is x squared. So when you square that negative number, it becomes positive. So this guy is not extraneous, so we include both of these values in our solution set. Here we have an equation, the two terms on the left-hand side. The first term contains my variable, so I want to get this term by itself, so it gives me a starting point. I'm going to add 7 to each side. Now, on the left-hand side, I have two factors. See, terms are separated by addition and subtraction, factors by multiplication or division. So with these two factors, the factor of interest contains my variable, and I would like to cancel this other factor. So to do that, we divide both sides of the equation by 9. The 9 divided by 9 cancels to 1, and 1 times anything, well, you get that same thing back. And for 83, well, I just wrote it as an improper fraction because 83 is not divisible by 9. We have an exponential equation. We've gone as far as we can. We need to take the log of each side. Now, when I say take the log of each side, remember I have the choice of choosing whatever base I want. And it's going to be smart this time to choose a base of e to take the natural log of each side. Because when we do that, with this base being e, you have this base of e and this base of e equal to each other. So on the left-hand side, this just simplifies to this exponent 4 minus 2a. Now on the right-hand side, when I took the natural log of the left-hand side to balance the equation, I had to take the natural log of the right-hand side. I can't do anything with that fraction, so it just stays there. Now I have two steps and I'll have the a by itself. I want to subtract 4 from both sides and divide by negative 2. When I subtract 4 from both sides, the 4 minus 4 cancels, and I'm left with negative 2a. Don't lose the negative sign that's in front of that 2. Since I subtracted 4 on the left-hand side, I had to subtract 4 on the right-hand side. Now, I'm going to divide both sides by negative 2. Negative 2 divided by negative 2 is 1, so I have 1a on the left, and this numerator divided by negative 2 there. When I go to the calculator and I key it in, make sure that you put the entire numerator in parentheses, and don't forget to close that parentheses when you're taking the natural log of this improper fraction. When I do that, my calculator came back and gave me a value of 0.8892. I had my calculator set up to round to 4 digits to the nearest 10,000th. In number 11, we have an exponential equation, and upon inspection we've got 27 and 9, so I know that I can rewrite these guys with a base of 3. I know that 3 cubed is 27, and I know that 3 squared is 9. So oh, wait a minute. Let's back up. I could have done that, and I could have jumped in right away to rewrite these bases, but what I apparently noticed when I was writing this up, this is just a different way to do it, that with this same base right here of 27, when you have division of the same bases, you can subtract these exponents. So I took this exponent in the numerator minus this exponent in the denominator. Now, you can see on the right that I did rewrite 9 as 3 squared. I am going to try to now get a base of 3, but look, I just was able to clear that fraction quickly, and over here I might have saved a few steps by just subtracting these exponents first before trying to rewrite with a power of 3, because we would have had power to a power to multiply the exponents. But here, well, I guess we still do have a power to a power, but it's a less complicated expression if we've done that subtraction. Alright, so hopefully you can follow that if you have this 2n plus 2 minus this quantity, then I have 2n minus 3n, which is negative n. I have minus a negative 1, which is actually adding 1. 2 plus 1 is 3. I have a power raised to a power, so I multiply the exponents. And every term gets multiplied by 3, so the negative 9 gets multiplied by 3, but so does the 3. And the same thing over here. We rewrote 9 as 3 squared. The exponent didn't change. It was negative 2n minus 1. It's still negative 2n minus 1. But since we have rewritten the base and now we have a power raised to a power, we multiply this binomial by 2, and I get this new exponent, negative 4n minus 2. The bases are the same, the numbers are the same, so the exponents have to be the same. And now here, this is just a linear equation. Get the variable on one side, the numbers on the other. So it looks like that I added 4n to both sides, and then I'll subtract 9, and I get a final answer of negative 11. You could plug it back into the left-hand side and get a number on your calculator. Plug in the negative 11 to the right-hand side. You'll see that the calculator will tell you it's the same number. So it does check. Alright, so now I have a log equation, not an exponential equation. With log equations, I have to be careful. I can't take the log of 0, and I can't take the log of a negative number. Sometimes my solutions provide what they call extraneous solutions. So whenever I see a log equation, I've got to check my answer. So I have two terms. The term that contains my variable, I want to get it by itself. The inverse of adding 10 is to subtract 10. We subtract 10 from both sides. 10 minus 10 gives me 0, and 11 minus 10 is 1. Now I've gone as far as I can go with getting the variable by itself. I need to rewrite this log equation as an exponential equation. The base is e, even though it's not written. It's implied because it's this natural logarithm, this ln. So a logarithm equals an exponent, so I have e raised to the first power is equal to 8 times x. To get the x by itself, we undo this multiplication. The inverse of multiplication is division. We divide both sides by 8, and we have our answer. Now, did I go to the calculator? Yes, I did go to the calculator, and sometimes it will ask you what exponent to put on e. Well, if you have to, just tell it key in an exponent of 1, and that will give you e to the first power, which is just e, and e divided by 8, I got 0.3398 if I entered that in correctly. Number 13 is a word problem. It was the airplane problem where you have a skydiver that's jumping out of the airplane. Now on the first review, they told us the output of the function. They said, hey, how long will it take after you've jumped out of the airplane to reach a velocity, I think it was 60 feet per second. So on the left-hand side of the equation, we replaced the v with the 60, and then we had that complicated exponential equation to solve. Well, this time it's different. They're not asking us to find the input. They're asking us to find an output. So that's going to be easier. All we have to do to find out the velocity after 3 seconds after you jumped out of the airplane is to replace t with 3. So on the left-hand side, this is just the notation saying the output of this function. When the input is 3, on the right-hand side, it'll give you that numerical value. Plug that into the calculator, and I got to 2 decimals, 42.07, and the units were feet per second. All right, I hope that helps, and I will talk to you later. Hey, before I sign off, I thought that you might like to hear about a math legend at Northview High School. One of our math students years ago was just so incredible at math that all the teachers gave him a nickname, BA, and another student in our 4th period class drew us a picture of this legendary math student, so I thought I'd share that with you. Here's the legendary math student from Northview High School, and hope you enjoy that. Talk to you later.